Hello, today we're going to be talking about forces, and this takes place in Chapter 3, Section 1 of our physical science textbook. So let's get started. What is force? Well, we need to know that a force is a push or a pull. Physics kind of boils everything down into those two forces. You're either pushing something or something is pulling you. And that is the definition of a force. We use force to change motion. Whether you're not moving at all, to get going, you need a push or a pull. If you're already moving and you want to change direction, that would be a different push or pull to change the direction of motion. A new force can cause the motion of an object to change. So once an object is moving, if you want to change direction, we need to actually put a new force to it in the direction that we would like it to go. The easiest way to think about this is when you play pool. For instance, in this pool cue right here, we want the striped ball to go into the corner pocket. So I want to put a force, a push, on the cue ball that's going to hit the side over here of this striped ball to cause the one ball to go into the corner pocket, and then my cue ball will then go in a different direction. So pool is a really great example for forces in all the different directions and things like that. It's a really wonderful game to learn about your angles and forces. The next topic we're going to talk about is net force. What is net force? A net, or is like the sum, it's all of the things that we're adding up. So net force, therefore, is all of the forces that are acting on an object. And almost all of the time, you have more than one force acting on an object, especially if that object is in motion. Forces are measured in newtons. We use the scientific method, and newtons is kilograms per meters per second squared, if I remember correctly. So force is mass times acceleration. So acceleration is meters per second squared, and mass is measured in kilograms. So if I said mass, I meant acceleration is meters per second squared. And that together, we multiply those together, so F equals ma. That is the formula for force, is mass times acceleration. And here is the breakdown of what 1 Newton is. It's 1 kilogram per meters per second squared. Next thing we want to talk about is balanced forces. A balanced force results in zero net force. Remember, net force is all the forces working on an object. If they're balanced, they're not going to cause any change in motion. If I have 5 newtons of force in one direction and 5 newtons from the other direction, this is a balanced force. There's zero net force, okay? So there's no motion change. For instance, one way we can look at that is these two people pushing the same amount of force on either side of the box. It equals 0. One is in a positive direction, one is in the negative direction, so therefore there is no change in motion. It's not moving. And these can be objects that are in motion as well as objects that are rest. Remember, if it's zero net force, then that object will stay moving at that same rate in that same direction. Okay. For instance, the falling raindrop. Once a raindrop hits the speed, terminal velocity, where it was not gaining any more acceleration due to the air resistance on it, it is at a neutral force. As it falls down, air resistance is putting a force above it, so gravity will continue to pull it down at a constant rate. The net force is 0, even though the raindrop is still falling. Also, a rock resting on the ground has a net force of 0 because it's not moving. The ground is pushing up the same hardness, the same force, as the rock is being attracted by the force of gravity, so there is no motion. An unbalanced force, this is what we like to deal with most of all because it's fun and exciting in physics, is a result of a positive or negative net force. All right, and these causes a change in motion, which result in positive or negative acceleration. Over here, I'll move myself so you can see we've got a net force of positively, two people pushing the same amount equals double force, causing the box to move in this direction. Over here, we have someone pushing really hard and someone not pushing very hard against her, so the result is a net force in that direction. Friction. What is friction? Friction is a force that opposes motion between two surfaces that are touching. We've talked about air resistance, how that's the resistance of an object moving through the air that the air doesn't want to separate. And it's very similar to friction, except this one is friction when two surfaces are touching. Now, let's say a hockey puck sitting on a tabletop, okay? So this is caused by the sticking or welding of microscopic surfaces, and we call these micro welds. These are the sources of the sticking or welding. When you look at atomic level, microscopic level of something that even looks smooth, we can actually tell that there are surfaces, actually variations in the atoms bonding themselves that cause imperfections, which is why typically when things are very smooth, very slick, they have very little micro welds, microscopic variation to cause them to be smooth. One of the reasons Teflon works so good is it fills in all of these little micro form indentations to create an actual very smooth surface, so there can be no micro welds. Static friction, there are a couple of different types of friction we're going to talk about, 3 different kinds. And these are important to know because it causes different things, and we use these things in physics and in our day-to-day life to do things. Static friction, this prevents 2 surfaces from sliding past each other. There's not enough force to break the microweld. It's when something is, you're pushing on it and it doesn't move, you haven't given it enough force to break that microweld contact. Okay? And again, there's no movement due to the balance of forces. So static friction, there is no movement. Now this picture right here shows another example of that. She's putting an applied force. Static friction is matching that applied force, so there's no movement. The box is staying still. The next type of friction that we talk about is sliding friction. This opposes the motion of 2 surfaces sliding past each other. They're actually moving, so as they're sliding past each other, it's that friction that you feel when you lightly move your hands back and forth. That is sliding friction. The applied force is enough to overcome static friction, and there's an unbalanced force resulting in movement. So we are moving with sliding friction. The force of sliding friction is usually less than the force of static friction, which means it usually takes more force to get it moving, and that makes sense. I don't know if you guys have moved like heavy box on carpet before, you kind of give it that hard little shove, and then once it starts to move, it's not as hard to push as it's moving. That's because sliding friction is less friction than static friction has. The last type of friction we'll talk about is rolling friction. Rolling friction is really kind of cool because what it is, it's static friction acting over a wheel. So as the wheel rolls, where the wheel is in contact with the surface, static friction happens right there and prevents that wheel from sliding on the surface that it makes contact to. But because of the fact that it's rolling, eventually that surface rises up and gets pulled away, and another part farther down the road gets attracted to that static friction, which makes sense when you stop to think about the amount of traction between, like, say, a tank-treaded vehicle. It has lots of traction. It doesn't slip or slide at all because there's so much static friction over that long area, whereas a wheel has very little static friction because of the tire. We also call rolling friction traction, and this prevents your tires from spinning. A spinning tire is a cause of the force rotating the tires greater than the force of static friction between the tires and surface, and then that actually is sliding friction. So when you're spinning your tires, that's actually sliding friction taking place on the surfaces between the tire and whatever contact that it is with. All right, so let's talk about gravity a little bit. There's a couple puns there, but I will resist the temptation. Gravity is an attractive force between any 2 objects. Yes, any object can actually have a gravity between them. The force of that gravity depends on the mass of the object and the distance between them. Obviously, the more massive, the larger the object, the more the force of gravity is going to be, and the closer they are, the more the force of gravity is going to be between them. Gravity is one of the 4 basic forces that we deal with. It's a constant. Okay, the formula is the force is the gravity, the big G this time, is the mass of object 1 multiplied by the mass of object 2 divided by the distance squared. Okay, and then there is a gravitational constant. We knew this formula a long time, but it took a long time to figure out what the gravitational constant was. That's what the big G stands for. It's a gravitational constant, and that is 6.67 times 10 to the negative 11th power Newton meters squared over kilograms squared. And we'll actually watch a video that talks about how they figured out this constant. This is known as the law of universal gravitation, and this formula can be used to find out how much gravitation any object can have. And you'll see the farther apart that distance, it's squared, so it reduces very, very quickly when you're dividing by the distance squared. And of course, Sir Isaac Newton is a gentleman that came up with the law of universal gravitation. So why do you feel the gravity from Earth but not from the sun? Well, if you paid attention and looked at that formula, it makes sense because even though the sun is much more massive than the Earth, the sun has a greater distance from us. And therefore, because that distance squared, we're dividing that, it's too far away to exert any gravitation on us, but it is large enough to exert gravitational attraction on the Earth, which is also pretty massive. So the force of gravity on Earth, it pulls us down at 9.81 meters per second squared. Now, you'll notice in this diagram here, the surface of the Earth and up into the atmosphere a little bit is 9.81. If you were to go inside of the Earth to a certain point, gravity actually will go up to 10.4 meters per second squared, and then it falls off because we're on the inner core, or inside of the Earth, and it's much less massive in there, okay? And then as we get farther away from space, we'll notice as the farther we get, the much less gravity gets in this expanding scale as it goes out. So the range of gravity, that means as the distance increases, the force decreases by a power of 2. And that's that d squared that we talked about on the universal law of gravitation. So again, if you double the distance, it's 4 times less the force. So it's 2 to the power of 2. So if we're quadrupling the distance, that would be then 4 squared, okay, which is 16. So we triple the distance, we're 9 times less force, okay? So that double, we take whatever that distance, how far it is away, and we square it, and that's how much times less force there is. Gravity is usually discussed as a field, but we know that it is actually rather a point because of how gravity works and the massive of it. It is a circular sphere, and so gravity is actually a sphere as well, and so it's actually a point inside that sphere, and it's not on a flat plane, which would be called the field. But we theorize it and think about it as on a plane to talk about the distance away and stuff like that. It makes it a little easier for us to understand. One thing that gravity causes is weight. Weight is the force that gravity exerts on an object. So the weight that you have is actually a measure of the force of the Earth's gravity pulling you down. Here's the formula for that. Weight is in newtons, and that is mass times the gravitational strength, or Fg, the force of gravity, is mass times its gravitational strength. So again, the force of gravity on Earth is 9.81 meters per second squared. This is a number that you will know, hopefully by the time we get done with physics and physical science. And again, remember, weight is different than mass. Weight is a force. If you look up here, we see weight is in newtons. It is a force, also the force of gravity. And it can differ depending on which gravitational body you're standing on. For instance, if you're on the moon, the gravity on the moon is much less than the gravity on the Earth. So you would weigh less on the moon. So everybody's like, ooh, I'll move there. Mass is how much matter we contain, how much stuff we have inside of us. That is mass. And we can also actually use gravity to find other planets because as we watch planets or different celestial bodies orbiting, there can be vibrations or different things that we can determine on light spectra and some other things that actually change when another gravitational body is nearby. And that is a lot of times how we find planets in distant solar systems as we watch for gravitation. And the motion of every planet in the solar system is affected by the gravitational pulls of other planets. And we can actually watch and see those micro changes in the light spectroscopy of different celestial bodies that we're looking at, and we can tell that there are different bodies attracting, and then we can use the force of gravity formula to figure out how massive those objects are. It's pretty cool. All right.